Good.
You weren't here, so
No, yeah,
I was like, I'm going to join,
okay.
Otherwise.
All right.
Okay.
Good. Yeah.
Good.
So, all right. Well, today's tutorial is about kinetic EFITs, and Katrina has kindly volunteered to tell us all about it.
Awesome. Okay, so today I'm going to talk to you about actually what is my favorite module, which is kineticEFITtime. And before we go into kineticEFITtime, first I want to talk to you about what you need to do before you open the module. This will end up saving you time later. So we've already ended up selecting a shot, and the shot that we've selected, you can see some of the waveforms here. So I'm using the pubfig within the scope module to make this. This is also one of the, when I'm making publication figures, this is one of my favorite ways to make them. So I know this has been talked about before, but just to show you what the shot is that we're selecting. So this is a shot that has some I-coil current. So we have an elm phase, and then we have a place where we're starting to get elm mitigation, and then we have an elm suppression phase. So what we're going to look at doing today is we're going to make kinetic EFITs during the time just before the I-coil current was turned on, and then once we enter the elm suppression stage. So from 2000 to 2800 milliseconds is the time that we've selected for this shot. Okay.
Mm-hmm.
So next I'm going to open up the kineticEFITtime tutorial. Now, so we've already selected a shot, we've selected a time. Now, what else do we like to do? So before I like to do this, there's two other things. The first one is you want to figure out when you're running an EFIT, you want to know what snap file you want. So you can look at that through EFIT Viewer. Outside of OMFIT, you can look at it with EFIT here just to make sure that there's no mistakes. So something that happened to me earlier is I actually had an earlier time point I was going to do for the shot, 500 milliseconds, and it kept failing. I couldn't figure out why it was failing. And because I was using EFIT02, so an MSE corrected EFIT, and the problem was because there was no MSE data.
Mm-hmm.
So that was a mistake. So that's something that is better to catch before you go into the process of making a kinetic EFIT. Or let's say you're missing CER data. That's something to catch before you actually go into the process of making a kinetic EFIT. Something that I personally like to do is I like to make a lot of kinetic EFITs, like hundreds of time points, which is a lot. And the way that I get around doing that before I go into kinetic EFIT is I actually run OMFITprofiles, the profiles, on a subset of those, so maybe like 20 time points, and figure out the settings that I need to set up when I'm running all the time points. Okay, so I'm gonna just doing file import.
And maybe when you import the module, for those who are not too familiar with the EFIT nomenclature, so EFIT is this equilibrium reconstruction code, and it uses some nomenclature for its files. So the input file to an EFIT is called a K file. The output of an EFIT is, there are many output files, but the most important one is what's called the G file, which is the file that contains the equilibrium. Catherine before was talking about the snap file. So this is a file. It's a kind of a special input file to EFIT, and it's a file that tells EFIT how to generate its own input file. So the K file that I talked about has experimental data in it, and it would be very tedious for anyone to do it by hand. So to fill it out by hand. So instead, what we do is we have this snap file, which basically tells EFIT, I want data from these magnetics probe. I want data from these flux loops. I want data from the MFC measurement. And when EFIT is run with that input file, it will generate a K file containing the experimental data from those diagnostics. Okay. And there are some standard snap files that we have at D2D. Different machines may have different ones. And usually we refer as EFIT01 as the EFIT that is only magnetics, with magnetics data, so snap file from 01. And EFIT02 is the one which has also the motional stark effect measurement, which measures the pitch angle of the magnetic field lines inside of the plasma.
So I'm going to import the OMFIT module, and the thing that I want to point out is there's actually two modules that start with kinetic EFIT. We're going to use the kineticEFITtime module as the one we're going to start loading. So the kineticEFIT was the module that was first developed. It was kind of and it uses GPEC, and that one is eventually the two will become merged, but you should use kineticEFITtime. You can use kineticEFITtime even with only one time point. So that's the one that I would recommend people use. Okay, now we're going to double click on the module to open up the GUI.
Can you maybe show us what's in the module?
Yes, that's so this is something that's important to know about kineticEFIT is that it has a parent module and has children module that can be run separately. So I've mentioned some of these already. There's EFITtime, which you can use to make EFITs. There's OMFITprofiles, which you can use to make profiles, and there's TRANSP and 1,2time, which are both transport codes that you can use to calculate the pressure and currents for your shots and get some of the transport coefficients. So this is the shot that I showed you earlier, and then this.
Both TRANSP and 1, 2.
We'll get to that when we get there. You have two options on how to do that, depending on what you want to do, and I'll talk about when you might want to use one over the other later. But so what we're going to do now is we have this time that I've selected here. Let me just show people how I got this. So I actually I used a Python command just to get a bunch of different times. That way I didn't have to type it out because it takes a while. This is really important because, as I said, sometimes I like to do 200 time points, and I do not want to write down every single one because I'm more likely than not to make a mistake. So now what we're going to do is we're going to figure out what snap file that we're going to use. So we're going to look at the MDS Plus database, what is available. And so the different trees I was talking about earlier in ORSA was the EFIT01 is the magnetics. And I said we're going to use the MSc and magnetics one, so that's EFIT02. And now we're going to generate the K files from the snap file. So this is the input files that we're going to use later when we make the equilibrium files.
And maybe one thing, oh yeah, there was a question.
What's happening?
Okay.
Right, maybe you can show us.
Yeah,
what's
well, I was
happening.
going to show you after it was done. So right now what we're doing is we're making the input files, but something that's important when you look at the tree here for EFITtime, you can see the inputs is now full. There's the snap file that I selected, but then if you open up the K equidist, this is the K files, you see that for each of the different time points. There's the different input files that are going to be needed for later on. Okay, so now that we have the K files, what are we going to do next? You see up here that we're now on iteration 0 is what it's called. And there's 2 steps in iteration 0. You can run the profiles, and then you want to run the equilibrium. The main point of iteration 0 is to get the equilibrium that you're going to use for your profiles later on. We're going to skip this run profile steps in this case, but you would want to actually run the profiles in 2 cases. Basically, if you wanted to provide some type of constraint for your equilibrium that you're going to use later on. So for example, if you wanted to constrain where the boundary was using the Thompson data for your EFIT, if you wanted to say, I trust my profile data is at this position, you would move your EFIT to that. Or the other way that I most often use this is I use this to do an MSc ER correction. So on the profile steps, I calculate the toroidal rotation, and then I subtract that off of the MSc data in the next step. So we're going to deselect this, and you're going to see that the profiles tab went away. So we're going to click on the EFIT tab here. And so what you can see here are the standard default settings that we're going to use to run EFITtime. So we're going to use a 129 by 129 grid. We're going to have a solution relaxation of 0.5. This can go from 0 to 1, so this is the average one. And then we're going to set a convergence error of 1e minus 3. And then we're going to have run for 25 iterations at each time point, at least, or until it gets to this 1e minus 3 constraint that we wanted. And then we can go down below and then see what's set up. And so if I had MSc data, if I had done the toroidal rotation in the profile step, I would click this button right here, and then it would be applied here, but I do not. And then here you can see that the pressure constraint is missing, and then the current constraint is missing. And this is because we haven't run any transport codes. We don't have any constraints. When we run EFIT again, we'll have these constraints back on. So now I'm going to go back to the main tab, and I'm going to run the equilibrium.
You could just take one of MDS Plus. I'm confused. I mean, you're just making standard EFITs, right?
Right now, yes. What the important thing is actually to get the K file, because what we're going to do at the later stage is we're going to add constraints to the K file that we have made at this step. So the K file, which again are the inputs to EFIT that we're using right now, they have no pressure constraint nor current constraint. And so right now you're correct, especially the way we are running it right now. We're not. This is a standard EFIT 2, so we could have got this from
But so, for example, something I like to do is like I use EFIT2 as a snap file, but I run it at like more often time points in MDS plus, like every 20 milliseconds, and sometimes it's only every 100 milliseconds. So that's why I like to use that.
Right, that's a good point. So, and the EFITs, the G files that we're going to get are exactly the times that Catherine specified.
Okay, so we have the EFITs have already been done. So now if we go to the plotting tab, so what I'm going to look at is I'm going to select all the times, and then I'm going to select iteration 0. And so when I'm here, I like to look at a couple of things. The first thing I like to look at is to plot the G files. And this is to make sure that nothing looks really funny, everything looks regular. When I was first learning how to do EFITs, I had one that was really funny looking and did not look diverted. It was just up here. And you can catch those type of mistakes by looking at your equilibrium here. So everything looks pretty normal. You can see that the equilibrium isn't really changing here. But then the next thing that I like to look at is I like to look at the chi-square as a function of time. So we have 9 time points that we're looking at. I want to see, is there any one time point where the chi-squared is a lot worse than the other chi-squareds? So on the top here is all the magnetics and the MSE data. So you can see what's comprising all the different ones. You can see it's relatively flat for both the magnetics and the MSE. So that's pretty good. I'm pretty happy. So this is like, this would call out if I had a certain time point that, oh, the EFIT there is just not doing very well. What's going on there? There might be a spike in the data. And something that, since I do so many time points when I'm doing kinetic EFITs, I like to know what the mean is. You know, that it helps guide the eye. And then here, the next tab is showing you what the error is. And so if you remember, we set the error to be 1 e to minus 3. You see that's down here. The red line is kind of where you have to be below, otherwise your transport codes will fail. So trans will give you errors. That's what I was talking about with the equilibrium. That's kind of funny up in the corner of the tokamak. But another way to look at this is what the mean is here. We can see that this is also less than 1 e to minus 3. And then down below, we can see what the z of the axis is. Where is it? You know, what's it looking like? Does it actually make sense for what we're doing? And then the next thing that I like to look at is I also like to look at the error. You might remember that we set 25 iterations and we wanted to get down to 1 e minus 3. So something that I like to do here is I like to go to the error tab. I like to kind of see like how many iterations did it take. You know, this is if I want to go to as we will when we're actually making the kinetic EFIT, we'll want the error to be lower. We want it to be 1 e minus 5, 1 e minus 8, depending on what type of kinetic EFIT you want. So you can see here to get to 1 e to the minus 3, it's about 12. So that means I have some room of the 25 that I could set it lower and I might get a little bit closer. So now we've done the EFIT stage, we're happy with this, and this is what we're going to use next for the profiles, to fit the profiles equilibrium we're going to use for our profiles. So we're going to go up here and we're going to hit 1. And when we hit 1, you're going to see that we have some new options for this is what we're going to do in the second round of steps. So when I'm doing this, I like to only do 1 step at a time just to make sure that I'm doing everything correctly. So I'm going to deselect the run transport and the run equilibrium. We're just going to focus on the profile step. So Nick gave a tutorial a while ago about the OMFIT profile step, so I'm not going to go into this in detail. I'm going to just set this to 1D fits time slices, which is what I'm used to. And when you're doing a kinetic EFIT, it's really important at this step, and this is actually where I think a lot of people spend the majority of their time is going through each of these tabs to make sure that you're doing it correctly. But for right now, for the point of time, we're just going to use the default settings. So I'm going to go back to the main tab where we have what you can do, and I'm going to hit run profiles. Okay, now while that's going, so this is the step that is probably going to take the longest. I want to open up a web browser. And what I want to do is I want to show the tutorial for this. So I never remember where the tutorials are. So what I usually do actually is I just go to OMFIT and I go to Google and I type OMFIT. And actually the first link is the most helpful link, which is awesome. And then when you're here, I sometimes get confused, but there's a Learn tab. And so the Learn is, I'm trying to learn about OMFIT. So you click on the Learn tab, then you're like, okay, what type of module do I want to learn about? And then you see the kineticEFITtime one is right up there. So I'm going to click on that one. Then I'm going to scroll down to where it says tutorials. And you see there's a tutorial both for D3D and for NSTX. I'm going to click on the D3D tutorial here, since this is what we're talking about. And this tutorial is pretty well written. It goes through all the steps, and it actually gives you something that you can do. So the first time that you're trying to run a kineticEFIT, you should follow along in here. You don't want to start with a new shot that hasn't happened before, because there might be something that's messed up with the data or the EFIT, and that's hard to catch if it's your first time going through. You want to have a success in the hand before you move on to actually analyzing your shot. So this goes through kind of what the principle is behind making a kineticEFIT and goes through the different steps that we're going through. And something that really helped me and like Orso and I had major discussions when I was trying to figure out how to make kineticEFIT, and we actually came up with this diagram here to kind of just understand what's going on. And so you see we have iteration 0, 1, 2. There can actually be more iterations depending on what you're trying to do. And you see that the 3 steps that we've talked about. So far we've talked about the equilibrium. Right now we're doing the profile step, but there's the transport step. And so you can see on the first round you can do profiles, but when we had the iteration 0, there was no options for transport because we didn't have an equilibrium to use on it yet. And we went straight to the equilibrium. And now you can see in iteration 1, which is what we're doing now, we're on the profile step. And then after we run the profile step, we're going to go to the transport step and run that, get the information we need to make the kineticEFIT, which is right here. And so after you have that, for some people, this would be good enough, because what do we need a kineticEFIT for? So there's a couple of different reasons why you need a kineticEFIT. And usually that's for either stability codes or transport codes. So for stability codes, that would be like ELITE, GPEC, Mars, DCON. You want to just have a really good equilibrium that you trust, and you can use in those codes. Now, it's what I actually like to use the kineticEFITtime module for is a little bit different. I like to use it to prepare my transplants. So I want to study, so what I'm trying to do is I'm trying to study how the transport changed in a discharge as a function of time. And so I want to have a transrun, or you can have 1, 2 time. I want to use that to analyze the discharge. And so I actually will sometimes stop here, and then sometimes I'll actually go to iteration 2 after I had the kineticEFIT and then have another transrun. And so different people have different uses for this workflow, which is kind of cool because it has a lot of capabilities, and I'm sure there's other capabilities that we aren't talking about as well. And so you can see it just goes through here and tells you exactly what you're going to do, a lot of what we've talked about so far. So this is a really good place to look when you're first trying to figure out how to run a kineticEFIT. Okay, so now let's go back to no machine, and let's see if we have all the information that we need from the profiles. Okay, so you can see we don't have something showing up, so that means that it's been run. So we're going to go to the profiles tab, and I always like to look at the end result in a module before moving on to the next one. I don't want to just hit, okay, I have my profile, let me go make the kineticEFIT, because there could be a mistake here, and then it's going to be a lot easier to fix it here than it is to fix it later. So what I'm going to look at here is I'm going to look at the plotting. So I'm going to plot the 1D static profiles of the different ones that we care about. Okay, and so this is going to plot for all the different time points that we have. It's going to plot the different profiles. See here, I changed my settings to make it the figures really big, so it's not really showing up. But one thing that's helpful is under the
just go to the
yeah, or what I'm just gonna go change the plot style. And so this is going to just plot each profile in a different tab. Okay, and so I actually prefer to have it this way because it's easier, I think, to focus on one thing at a time. But if you want a global perspective, you can do the other one. So here you can see we have the density, the electron density, the temperature, and all the different ones we care about for the different times. So I'll just scroll through these. Right now, we haven't gone through the channel selection. We haven't made sure that there was anything that was wrong in these cases. But now let's look at the electron temperature. This is one that I like to look at a lot. For this case, you can see that the foot of the pedestal is almost at row 1. There might be some small corrections that we're going to do, and I'll actually walk through that. Here's the radiated power. You can see, that looks relatively okay. If I was doing this for real, I would actually be more I would check the bolometer channel selection that's going on here. See the ion temperatures, those look pretty good. The toroidal rotation, and then the ion carbon density. Okay, so now the one step that I said that I wanted to do again is I wanted to look at the Thomson separatrix. So this is something that Nick went through in his tutorial, where we're going to go up here to the Thomson tab, and we're going to look at this compute and plot the separatrix location. So on D3D, since the Thomson system is vertical rather than horizontal on the midplane, there's a problem. We need to either shift our profile data to have the foot be at row of 1, or we need a constraint EFIT to be at row of 1. So there's a bunch of different constraints that you can see here. Different charges require different constraints. Also depends on what type of analysis you want to do it, which one you think is better for that particular shot. So here you can see the first time point and the last time point showing up here. And then if we go to what the Thomson data is being shifted, what is it actually going to do when we do this is what I like to look at. So you can see the dash versus the solid lines, that you see the solid lines are a little bit more lined up and they all look very uniform. So I'm going to end up shifting this. So instead of doing the form constraints for EFIT, what I like to personally do is I usually shift the diagnostics and OMFIT profiles. So that's what we're going to do here. And then I'm going to apply this separatrix workflow based on the electron temperature. So I'm going to click this button, and so this is just going to take my electron temperature and my electron density Thomson data and shift them. But since I've shifted those data points, what I need to do is I need to refit those data points. So I'm going to go back into the fit tab, and then I'm going to go to electron temperature, density, and then temperature, and I'm going to fit those. I could hit the fit all button up top, but it's faster to just hit the 2 that I needed, and you can see it's already done. See, that looks pretty good. Now we're going to go to electron density, temperature, and we're going to do the same thing. We're going to fit, and we're going to plot it. Okay, that was done really fast as well. Now there's one thing that's important to do. So in OMFIT profiles, what Nick talked about is there's the fits, but there's also the derived quantities, which depend on the fits. So I've fit the data, but since I changed the 2 fits, I need to recalculate the derived quantities. So I'm going to do that right now. Okay, and so this is going to run pretty fast. And if you might have noticed when we were at post-fit, there's a certain derived quantities that I could select. Now, I think probably one of the most common mistakes, and I've made this countless times, is you've noticed that I haven't been in the main tab hitting run profiles. I've been within the OMFIT profiles module hitting certain tasks. So it's really important when you're doing that to make sure you hit this button here, this update profiles for kineticEFITtime iteration 1. Because we talked about the tree before, there's the different modules, EFITtime, OMFIT profiles, 1, 2 time, but then there's also the outputs for the kineticEFITtime. So if we go into the outputs, there's iteration 0, which we started with, and then there's iteration 1, which we're on right now. But the iteration 1 that's in here is different than what we actually have in the OMFIT profiles outputs right now. And that's because this is only updated when we are from this main area, we hit the button here. Or if we're in OMFIT profiles, we're actually just going to hit this button right here. And then the outputs that was in the OMFIT profiles here is now going to be saved in the main outputs of the kineticEFITtime. It's just super important to make sure you do this, because otherwise you lose work.
The idea is that the pattern module has no way to know if you're doing something in the child module. And so if you mess around with the child, if you start clicking buttons that are inside of your OMFIT profiles GUI, it's okay, but then you have to make the pattern module, which is kineticEFITtime, aware of the changes that you've made. And so we do that by clicking on that update profile.
So now, just like we did before, I'm going to once again look at the profiles, make sure that they look sensible. I'm going to focus on the electron density and the electron temperature profiles. There you can see those, and then if you look at the electron temperature, so then you can see those. So maybe this one time point I'm not as happy with, but you can see the other ones are more lined up than before. This is something that you can play with, iterating back and forth. But for now, I'm going to be fine with this, and I'm going to move on to the next step of the kineticEFITtime. So I'm going to go back up to the top, go to the main tab. I'm just going to deselect run profiles, and then I'm only going to run transport. I think it's another reason why it's important to only have one module selected at a time is the GUI only has to load that one module, and the more GUIs you have loaded, the slower this is. Now we're going to go to the 1-2 GUI, and you see everything is set up here. Sterling, do you want to talk about the 1-2 time module and what all these different options are? I'm going to form this, but while we're doing this, that might be something that you can talk about.
Sure. So the 1-2 code is it's just it was a transport code written here in General Atomics, similar to TRANSP that Brian Grierson talked about last week. And one of the main purposes of running a transport code in this kineticEFIT process, there's 2 points. One is to get the total pressure, including the fast ion pressure. The other point is to come up with a calculation of the bootstrap current, which is an important contribution to the edge current. So the options here in the 1-2 tab are to update the profiles, the NBI and the ACH and the N1 files. And so if you've already done those things in a current step, then you don't have to repeat them in a future step, and you can unclick them in a future iteration. But for the first iteration, for the first time you're forming 1-2, then those need to be set up. On the mode, the relax, you want to relax the current so that at the edge the current will not have some odd ohmic spike. The other options are snapshot analysis, which is not evolve the current, or to evolve the current. So relaxed current and evolved current are very similar. It just depends on whether the timestamps of the files at the end.
So this is completed, and now, as always,
Wait, so that formed the N1 files.
formed.
So if you go under 1-2 time, for example, the module in the tree.
Okay. Yes.
Under inputs, E1. Then you see the input file for 1-2 for all the time.
Okay.
And so on. And you can run 1-2
On the main tab.
Okay. I see what I did. Okay, so, and I'm going to run the transport code here, but you see this transport module we selected 1-2, that is the default for D3D. There is also the option, if you click here, to run TRANSP, and that's what Brian talked about last week. It depends on what you're wanting to do and how many time points you are, but as you'll see, 1-2 actually runs in a pretty fast manner. So if you're trying to do a few time points and really get a kineticEFIT, and if fast, this is something that you would want to run 1-2, or you could run 1-2. The other option is to run TRANS. I usually like to run TRANS, but that's personally because I usually want to know what the transport is doing through the shot. But that takes several hours, and there's a lot more options there that Brian talked about last week. But so you have the option, depending on what you want to do. You can run 1-2, maybe the first iteration, and then maybe the second time you want to run TRANS. It gives you that flexibility on what you want to do.
Catherine, are you running it time dependent or just snapshots at each time, each of those 10 times?
We are running snapshots of each of those times.
They're not exactly snapshots, because each one of those time slices, we're letting the current evolve for a few milliseconds. So it's a series of evolving TRANSP simulations. Sorry, 1-2 simulations, but with very short current evolution.
So right now what is happening is we've dispatched this job, and you can see that there's a bunch of different processes that are running on the Iris cluster. We're waiting for them to finish for them to run 1, 2. Now another mistake that I like to make is I always forget to save my project. And I think the most important time to save your project is after you've done the OMFIT profiles, because that's the time that you spend the most amount of making sure your profiles are exactly right. And running 1, 2 or running EFIT, those don't take as much time. I mean, it's important to regularly save your project, but I always try and really remember to save my project after I made profiles. So you can come here, you can save it in the background. I often forget to save my project until this step, and so I do file save as, and I can also save that in the background. So it's nice that I can have this code going, and I'm also starting to save the project at the same time.
Any questions? So maybe again, stepping a bit back, maybe we should have even said this at the beginning. So a kinetic EFIT is an equilibrium reconstruction that is not only constrained by the magnetic measurements. So the problem with reconstructing an equilibrium with only magnetic measurements is that some of the quantities that are inside of the plasma, they are not well defined. So global quantities like the global pressure, so beta, and the current distribution, so Li, we can capture well with only magnetic information. But for example, the pressure profile inside of the plasma or the current profile inside of the plasma and actually are pretty much arbitrary. So if we want to get an equilibrium which is sensible in terms of the pressure profile and the current profile, it is mandatory to do a kinetic equilibrium reconstruction. What the kinetic equilibrium reconstruction adds, we'll see, are constraints for the pressure and the current profile inside of the plasma. So the idea is that you have some ways of knowing what the pressure profile and the current profile should be in the plasma. And so when you're doing your equilibrium reconstruction, you tell me that, when you're doing the reconstructions, use also this additional information. Getting the pressure and the current information in the plasma is not too trivial, and you can get to get the pressure, you have to have the density and temperature measurement for the different species that are in the plasma. One of these species can be a fast ion. So the neutral beam, that we inject into the plasma. Those ions can have are very low in density, but they are very high in temperature, so they can have a significant contribution to the global pressure. And so this is why we had to run a transfer model as part of this process, because the transfer model has a neutral beam model as part of it, and so this allows us to have all of the bits and pieces that we need to in the end constrain the equilibrium reconstruction.
So you can see that we're finished. 1, 2 is finished running. So we're going to go to the 1, 2 tab. You can see that things have changed. Some of the boxes have deselected. And you can see we now also have an option to plot. So let's take a look at the state files and see what is the output that we got from 1, 2 here. Okay, so we have a bunch of different plasma parameters which were input. So what Orso was talking about, we have the current density. So each of the different colors represents the different time points. On the top here is the total current that 1, 2 is calculated. And then you can see what the fast ion current is. The bootstrap current is down here. Then we have the temperatures, we have the electron and the ion temperatures, and then we have the different densities, the toroidal rotation, the safety factors, and we have the different diffusivities, the ion and the electron, and then we have the main ion particle flux and the rotation flux that 1, 2 is calculated as well. Okay, so everything looks good there, and we're going to go back to the main tab. We're going to deselect the run transport. We're going to now run the equilibrium. So this is now when we're actually going to get a kineticEFIT. So now when we go to the EFIT tab again, we're going to go down, and we're not going to use the boundary constraint because we've already moved the diagnostics. So we're not going to constrain it two different ways. We don't have the and we don't, now we can actually correct the MSE for the radioelectric field because we calculated the profile data. But let's select that. And then we can go to the pressure and the current constraint. And you can see these are automatically set up. So this is, we now have, what we run 1-2, we've run a transport model. We now have the pressure constraint. So we now know what the fast ion pressure is. We didn't know that when we were only doing the profiles and the current. We now know what the bootstrap current is in the edge. That's not something that we're able to measure. We have diagnostic data for motional stark effect on 3D that's pretty good inside of about rho 0.6. So we can have the current constraint very well there, but outside of that, we don't, it's harder to constrain the current profile. So we're going to use those. So I'm going to change the convergence error. So this is the kineticEFIT. We want to do better than 1 e to minus 3. So I'm going to set 1 e to minus 5. You can change this depending on what you want to do. But let's just get that going because this will take a little bit of time. So while we're running this, we're going to, again, this is what we're doing is we're dispatching, we're setting it up, and then we're going to dispatch the job to a queue to start running. And then you can see that it's running in the background here. And now let's talk about the different constraints because you saw that there were some options when we looked at the pressure and the current constraint. So this is if you're trying to get a really good kineticEFIT, this is where you would spend a lot of time adjusting, seeing how you could change it to get a really low error. So now first we're going to take a look at the pressure constraint. And for the pressure constraint, we don't have it biased towards the edge or the core. We're having it constrained to the pressure as a whole. So now when we look at this graph, the solid lines up top here are the total pressure, and the lines just below are the fast ion pressures, the dashed lines here. So you can see that the fast ion pressure is not insignificant. It does make about a quarter, a fifth of the total pressure. And then you can see the error bars here, those are the error bars for the different times. So the yellow is one of the earlier time points, and the purple is one of the later time points. Okay, so this is what the constraints are for there. So you can see that the error we have here. And now if you might have noticed that there's different errors that you can specify. You can say the uncertainty is a fraction of the total pressure, and then you can say it as a fraction of the fast ion pressure, depending on maybe you want to do some, maybe you're doing some fast ion studies and you want it to be constrained very well for that. That's something that you would click there. So you could change the value.
One thing to understand is that the contribution of the fast ion pressure, especially, is the result of the model. And so, what is the uncertainty on that? I think is up to fundamentally you to decide. One thing that we could improve this module with is probably propagate the uncertainty from our experimental profiles to here. But at this point, we're not doing it.
So that was the pressure constraint. Now the current constraint. Let's take a look at the current constraint that we ended up using. So you can see here the current, and then the red dots is where we're constraining it. So for these plasmas, what we're doing, what the current setup we have here, this bias towards the edge, we see it's 0.6. It was 0 for the pressure. And so for the pressure, it was across the entire plasma. Right here, the red dots, what we're constraining it is we're constraining it to get the bootstrap current at the edge, and then we're constraining it all the way into where we think we can trust the MSE data, where the MSE data is constraining the current more inboard of the plasma inside of rho 0.4, 0.6. And then we can change this depending on what data we have available for that particular shot. And then let's say that sometimes you want to have more points that you're fitting, or you want to change the weight of the current constraint when you're running EFIT. Those are all options that you have the capability of doing here.
Can you show us?
What's the weight of the current constraint?
So for the pressure, there is an uncertainty, and I think the idea is that the pressure is comes from a measurement. besides the fast time pressure. And instead, the current, yeah, I think the assumption with it is that it is only the result of the model. And so EFIT itself doesn't allow you to specify an uncertainty. Instead, what EFIT allows you to do is to give it a weight. So you have this only, and this weight is not even a function of radius. It's like the total weight for how much like fast or your current. So when you're doing these equilibrium constructions,
one mean?
it's relative. One is greater than 0.1 and less than 10.
So there are the other inputs for EFIT, which are like the magnetics and the MSE and the flux loops.
Correct.
And each of them also have a weight.
Presumably that's inversely proportional to the error bar.
No. This is the weight of that measurement, which is independent from the uncertainty.
So the idea when you're doing these reconstructions, it's like having a blanket that is too short. Okay, so you can you want to cover your feet and you want to cover your chest, and you can choose what to cover by the weights that you give to your feet or your chest. Okay. So you have a bunch of observations, and you are giving each one different weights, and the output, the output of EFIT will reflect these choices that you're making. So let's say that if we cranked up the weight of the current constraint to 10 or 100, then EFIT will try very, very hard to match the current profile that we gave at the edge, at the expense of, for example, what the magnetic probes are saying, or what the MSE is saying. So, and what is the perfect melange of weights? That's the art that is behind making it with kinetic EFIT.
Is the number of points also effectively changing the weight?
I would assume so. I assume that if you give 1 point is effectively giving 1/60 first of the importance of the current weight.
Or like 30 points is the same as 0.5 in weight.
Perhaps.
Well,
So yes, I think that the number of constraints changes the effective weight of that type of constraint overall.
well, I don't know, maybe it's this kind of same question, but so now I see you have 61 points where you constrain the current adjustment.
Mm-hmm.
So is the weight of one applied to each of those points or
To each one of those. And again, the weight of one is a relative amount with respect to the other constraints that it is getting. Could you please show the basis functions? So this is an important piece of the for EFIT. So what EFIT is doing is it's solving the Grasha-Franz equation. Okay, and what it does is it assumes a functional form for the pressure, or P prime, actually the pressure derivative, and FF prime. Okay, the result of EFIT will be strongly dependent on what functional form you use to represent these two quantities. Okay, so there are different choices that one can make, and for example, one can choose. So for example, a functional form could be a polynomial representation. When we are doing kinetic EFITs, we're using spline representation. Let me go back to that. So what EFIT is doing is it will given some knots location, okay, so before we start EFIT, we assign some knots or some spline knots as a function of radius, where we say that these are, these knots are the knots for the spline representation of P prime and F prime. And what EFIT will do is it will try to change the coefficients of the splines at those radial locations in order to, solve the Grasha-Farnoff equation with, in agreement with the constraints that we give. Okay? So the big question here, the $1 million question here is, where do you put those knots? Okay. So if we put, for example, one knot is obviously on axis, and the other knot is obviously at the separatrix. Let's say that we put a single knot at mid radius. Okay. No matter what EFIT tries to do, it will never be able to capture the sharp gradients and the detail of the boost-up current at the edge. Okay. So one point in the center is not a good idea. So let's try, let's have 2 points. Okay. Let's have 2 knots. Okay. And you can keep on doing that. The problem is that if you put too many knots, if it has too many degrees of freedom for the number of constraints that it's given, okay? So we want to give the minimum number of knots that we can give in order for it to be able to represent the structure that we want for P prime and F prime, but no more than necessary, okay? So what OMFIT here is doing is it's using, it's calculating what the P prime and F prime should be based on the constraints that we have given. And then it's placing the knots in those locations. Can you step through maybe a few times? So basically, we're making a guess that if we want EFIT to reproduce the pressure and current constraint that we've given, these are really the best knots location that we can give it, so that EFIT will have the freedom to reproduce the constraints that we want. I hope okay. So you see those points are the knots, and they're moving around, yes. And the red line is reproducing in a relatively decent way the blue line, which is the constraint that we're giving.
So it's not forcing P prime to vanish at the axis.
Correct.
Why is that reasonable?
Because this is dPd psi, not dPd rho. There's no physical constraint on it.
There's that option to force P prime and axis.
Yeah, there
you could force it there. Yeah, you could force it to be zero state. Yeah.
That red line is also not the P prime that actually happens in EFIT.
Right. So this is the best guess that we have, this is if you take a spline and you make it go through the red points, how well can it match the blue line? But we haven't run EFIT yet.
EFIT has its own internal use of these knots.
Right. Plus, EFIT also will be aware of all of the constraints, magnetic constraints, MSC constraints, current constraints. What we're doing here is we're kind of giving EFIT the freedom to reproduce the blue line, given the number of knots that we've chosen.
Okay. So while we've been talking, we've actually already finished running EFIT. So similar to what we did previously, I'm going to compare our different iterations. So the first thing I want to do is I want to just see how the chi-squared changed between these 2 different iterations. So we have all the time points selected, and we have both iterations selected. Okay. Overplotted. I'm going to close both rules. Plot again. Okay, so we have, you can tell which iteration it is by the corner note on the right. So this is iteration 0. And this is what we looked at the first round. You can see what the chi-squareds were, what the error was, and what the z on axis looked like. And now you can see on the right what has happened. And so one thing you might notice when you compare these is the chi-squared numbers has gone off in iteration 1. You can see that this is particularly true for the MSC, and is also true for the magnetics as well.
And again, this is not surprising. Okay, going back to the blanket analogy, we added more constraints, and so sure, the magnetic error has gone up, but now the pressure is doing what we think is physical. So we pull our blanket more towards the pressure, and therefore it increased the error somewhere else.
But one thing that you can see is if we look at the error when we reached iteration 0, it was 9.4 e to the minus 4 for the mean. Now it's 1.9 e to the minus 4. So we wanted to get down to 1 e to the minus 5, and you can see that we didn't quite get there, but we did get lower. And so now that we have this, I want to take a look and see how the error changed for these two. See how many iterations did it take. Did it run all 25 to get down there? That's probably my guess. And you can see that for a lot of them, it did run to 25, and it kind of, it was still going. So this gives me an idea that maybe if I run for 50 or 100, it might get, the error will probably decrease. But then we can also, there's some other options that we've talked about on how to decrease error. So one thing that I, for example, like to take is the solution relaxation. If we hit the question mark, it tells you between 0 and 1. So right now it's set to 0.5. If you set it to, I sometimes will set it to 0.7 or so, and then it might run slower, but then it'll converge. It'll have a lower chi-squared and lower error.
Can we show the difference between?
Oh yeah, that's why I haven't gotten there yet. But this is just showing you options that if you're trying to get a really good kinetic EFIT, there's a bunch of different utilities in here that you can play with. Now first let's take a look at two different, instead of looking at all these times because it's a little bit hard to look at all these times, let's just pick one time. We'll start with 2200. So this is before we had the Elm suppression. We're going to take a look at the G files. So this is going to compare the equilibrium and then the different profiles. When we do this, we can see that the equilibrium didn't really change here. But then if you look at the pressure profile, you can see for iteration 1, which is the green here, that we have more of a pedestal foot that was actually showing up. And then, yeah, I'll change it back to the normal because it's set to default. Let's try this again. So this is what I was saying, just to show it again. We have a pressure pedestal that actually shows up in iteration 1 because we've applied the kinetic constraints that we didn't have when we did it the first time in iteration 0, which we only had the magnetics and MSC constraints in the core of the plasma. And then something that we can also take a look at is let's look at different time points just in iteration 1. So let's look at 2200 and then 2800 and see what's the difference between these two. What did the effect of applying this I coil do to the plasma? So now if we look here, we can see that at the earlier time point, we had a higher pressure, more about pedestal, and then at the later time when we had the Elm suppression, you can see that the pedestal decreased and the pressure overall decreased during that time. Now, after you've done, after you've made really good kinetic EFITs, something that you have the option of in the EFIT module is you can actually export these. You can save these to MDS Plus. So you can use them outside of OMFIT. So if we click Save to MDS Plus, what happens is we get an IDL script that pops up, and we can write the module. And so this is just like it would be if you were using IDL and you wanted to save your EFITs to MDS Plus, you could fill this out and you could load it that way. I'm not going to do that because these aren't particularly good kinetic EFITs, but it just shows you that you have the capability to do so. So that was all that I wanted to cover. So if anyone has questions.
Go ahead. Suppose you want to use the odd bits like that profile fits. How do you? I mean, it might be outside of this tutorial, but
Yeah, it is.
If you want to use Tom's tools profile fits to form the do what?
Instead of
the
OMFIT.
profile, so you wouldn't go through profile fitting.
So right now, kineticEFITtime only works with OMFITprofiles. You can compare with GA profiles and Tom's tools, but that is a capability that people are
So
working on
I think that
loading them
I
in.
think the kineticEFIT module can load in the the Osmond profiles, but it will do it for a single time slice. So the original kineticEFIT module was designed to work with a single time slice, and when it was when we first developed it, we're gonna have OMFIT profiles. So we relied on the existing tools for profile fitting, which means GA profiles, ZFITs, and Tom's tools. Since then, I think as soon as people started, being able to make one kineticEFIT pretty easily, the appetite for having many time slices, came, and so we had to kind of start over, and that's what we came up with. For example, Catherine uses often, several hundreds of time slices for her analysis. If you're interested in a single time slice, you could try the module. Although it's not that well supported, I would say anymore.
Yeah.
I think that in the future, it's something that will hopefully be added, that as well as
We
GA
could,
profiles.
We could, yeah.
Yeah, if there's a use case where you think you have, tens of profiles from Tom's tools that you need kineticEFITs for, we can work with you.
Well, I mean, we struggle with kineticEFITs. We have to get to -8 here, so there's a lot of struggling there. So I'd be curious if this would do better, or was that the same?
I think all we're doing is we're wrapping something that you're already doing. So if you're struggling, I don't know that what we would be changing anything that you're already struggling with.
If you look under profiles, there is a compare, right? You can compare the results of OMFIT profiles with some fits that you may already have in GA profiles or in Tom's tools.
So, okay, another question I have. So I remember you once demonstrating, you had some GUI for looking at, I think you had equilibrium, and you had like some way of looking at chi-squares of different magnetic probes and stuff. Is there some pictorial way of seeing where big chi-squares are coming from?
Right.
Yeah.
So if you right. So can you go back up a little bit?
Yeah.
So before Catherine was clicking on the plotting tab, but there is also a plot tab under the EFIT tab, and that has a bit more or a bit different options. So for example, you can you can pick a time, add it, and then you can plot the G file, the flux surface information, or which is the same plot that we kind of saw before, or you can plot the chi-square. And I think this is the plot that you were referring to.
It's a very detailed plot, so you have to be careful to only pick one. Otherwise, you have 20.
Yeah,
you have
well,
a time point for each one.
I mean, I wonder if this could be very useful.
So, so here, if you look on this plot, the stars are the MSE. So if you if we look at here, you can see that there is this. Oops, I need to click. There is the one MSE channel that has a very high chi-square. So probably if we turned off this particular channel number 2, you know, for some reason it has a very high chi-square, we may be able to reduce this one.
That's pretty far inside.
One reason for which, you know, the MSE in the very core could be off is because your magnetic axis is not exactly right. So maybe your total pressure is not exactly right. One way to lower the MSE chi-square would be, for example, to increase the uncertainty on our pressure constraint. Let's say that you have a lot of fast ion losses. You know, maybe you know that in the plasma there are, you know, some eigenmodes that are increasing the fast ion loss. So then you could increase the amount of uncertainty on your pressure, and that will, you know, basically, if you would pass more the MSE in the port.
Yeah, I mean, I know there's a trade-off between them.
Correct. Correct.
So one other question is, so when you hit the bootstrap current, it's used to saute well, or do you have came up from needle? I mean, it seems like once you talk to somebody, when we're letting some needles,
Right.
get better results in some cases.
So right now, the kineticEFITtime only runs the Sauter model that is in 1.2.
Or TRANSP, whatever's
Or TRANSP.
Yeah, and TRANSP also uses this.
By default. I think you could even turn on NEO.
It's not available in the module. I think you have to special permission.
Okay.
So
there was an idea of, I think, start using NEO for this workflow. And it's something that we haven't done yet. If you want to use NEO, again, that's a capability that is in the original kineticEFIT module. But you know, when you're dealing with a single tenseless, everything is a bit easier. So,
yeah, maybe such
also, we developed a neural net version of NEO, which works particularly. I mean, it was tested with the D3D data. So that's also that will be also another option. I think it will be a very good application for it.
So when you're going through the steps, forgive my ignorance, I thought we had at one time some consistency, like to compare the stored energy between different iterations and also the those gone by the wayside.
That's in TRANS when you compare the TRANS experiment with that you have.
So basically, I need to add that in the 1.2. Got it.
Good question.
You're sorry you asked.
Are there any questions off-site?
That's clear.
Okay.
Yeah, and often, like Catherine said, you know, this is the starting point for more analysis. So what one could do is actually, can you show us in the EFIT in the tree? Where are the results? Under outputs, here are your famous G files that contain equilibrium information. And as Catherine said, you can go through multiple iterations. One reason you may want to do that is because you just updated your equilibrium, right? When you did your profile fitting, you were mapping your diagnostic data to an equilibrium. Now you updated the equilibrium. You may want to refit your profiles again based on the equilibrium that you just created. And so you can go, from iteration 1 to iteration 2, 3. But this process should converge pretty quickly. So the difference between 1 and 2 should be very small with respect to 0 and 1. And all of those iterations, again, they're saved under kineticEFITtime outputs. And then there you can see the different modules. And for each of the modules, you would have inputs and outputs. And so all of those can be, saved to, the file if you want.
Yeah, will you right-click on one of those trees? You should deploy as.
So, for example, maybe not on OMFITprofiles, but if you go to EFITtime outputs, and let's say that we want to dump all of the G file, A files, or let's say all of the G files, if you right-click and you say deploy as, your screen is small. Scroll down. You say deploy as, and here you can pick a directory. It's probably not there. So actually, the way this works is that here is the browser, and here is where you're going to download, where you're going to save your data. If we say G files, so this will take all of these the content of this GPEC directory and put it into your home directory G file. And so so all of these have been moved there. And now if you go to that folder, well, actually. You can find your G files there, and this works with fundamentally everything inside of OMFIT. I think that's it. It was a good 1 hour run. Yeah.